set that equal to 0. So I'm going to get 4 feet times L. That's the moment of this force. That one acts through B and has no moment. So this one is 4 times L. That one is going to be 8 times L. The next one is going to be 12 times L, 16 times L, and 20 times L. So that's those 5 loads. And then minus 20 times AY, sum of moments equals 0. And that is going to give me that AY is equal to 3L and BY is equal to 3L. Seems reasonable. Loads are symmetrically applied across the top. The supports are equidistant from the center, so they should carry an equal amount of load. Once I have the support reactions, I could throw all of the two force members away, draw the free body diagrams of all of these joints, and solve it. But the more members, the more joints you have, the more work that involves. And if I'm only interested in maybe one member, then I would like to maybe keep this as simple as possible. So, yes?
Should I be AY plus BY minus 6L?
AY plus BY minus 6L, thank you. Yeah. So 6L plus, I'm sorry, AY is 3L, BY is 3L. 3L plus 3L minus 6L equals 0. So that's the way it's supposed to be. When we do the method of sections, instead of breaking this down into 100 different pieces, I'm just going to cut a section through someplace and divide it into 2 big chunks and treat each of those 2 big chunks as another rigid body. Yes, it's made up of a bunch of 2 force members and pins, but who cares? It's just a rigid body as far as I'm concerned. And I'm going to cut it through the members. So as I said, no matter where I cut it, whether I cut it close to a joint, in the middle, or someplace else, the force at the point I cut it is still going to be along the member. I would really like to cut it through the member that I'm interested in. The problem that I run into, though, get this drawn. So 3L, L, and L. I'm going to cut it someplace between E and D, someplace between F and G. So E, sorry, this one is E, this one is F, A, and that joint doesn't even have a label on it. I'm going to have forces in the members that I cut through. So I'm cutting them someplace in the middle, not necessarily exactly in the middle, but someplace in the middle. The forces are still along the members. So this is going to be a force along the member ED. This is a force along the member DF. And this is a force along the member FG. Treating that as a rigid body, I get 3 equations of equilibrium. Sum of forces x equals 0, sum of forces y equals 0, sum of moments about some point equals 0. I get 3 equations. I can solve for no more than 3 unknowns. So when I cut the section, I want to cut through no more than 3 members of the truss. Get 3 unknowns. I would really like to have DG to be one of those members. But to cut through DG, if I cut through this way and cut through DG, I'd have to cut through 4 members. If I cut through this way, through DG, I have to cut through 4 members. So I can't get there directly. I do the next best thing. I cut someplace close to the member that I'm interested in and draw the free body diagram. Now you can either draw the free body diagram to the left side of where you're cutting it, Or you can draw the free body diagram of the right-hand side. The forces are going to be equal and opposite on the two parts. So choose the easiest one. This one is bigger, it has more forces acting on it. This one is smaller, has fewer forces. This might be the easier one to work with, the easier one to analyze. So what are the three equations? Summing forces horizontally. I get TED plus TFG plus TDF times the cosine of theta, if this angle in here is called theta. Sum of forces equals 0. Summing forces vertically, I get 3L from the support reaction minus 2L. The other four applied loads have all been thrown away with the part that I threw away. And then I get plus TDF times the sine of the angle theta, sum of forces equals 0. Two equations and three unknowns. Actually, it looks like I can solve for TDF at least from the second unknown, or from the second equation. So let's go ahead and do that. TDF is going to come out to be negative. 3L minus 2L is 1L. Take it to the other side, it becomes negative. So I'm going to get negative, well, what's theta? We've got a 3, 4, 5 right triangle. This triangle in here is 3 by 4 by 5 in theta. So the sine of theta is going to be 3/5. The cosine of theta is 4/5. Theta is the angle whose tangent is 3 divided by 4. Theta is going to come out to be 36.870 degrees. But sine theta is 3/5, so TDF is going to be 5/3, or 1.667 times L. Pounds or kilonewtons, depending on, I guess we're 4 feet. We're in English units, so it's going to be pounds. Even after I know TDF, the other equation still has two unknowns. I can't solve for it. But since we now have a rigid body, all of the forces do not pass through a single point, I can take moments. What point should I take moments about? I don't want to take moments about A, because that is a location of a force I know, and the forces I don't know all have moments about point A. Choose a point that gets rid of some unknowns. So point F would be a good point. Point D would be a good point. You do not have to sum moments about a point on the physical body itself. I can sum moments about a point D, even though it's on the part of the body that I threw away. So I'm going to choose to sum moments about F. If I take the sum of moments about F, neither of those forces have a moment. The L here does not have a moment. This L does. So I'm going to get 4 times L. That's the moment of this force. And then I'm going to get minus 4 times 3L. Those two forces, none of those have moment. The TED does. So I'm going to get minus 3 times TED. Sum of forces equals 0. So that allows me to solve immediately for TED. And TED is going to come out to be negative 2.67 times L. And now that I know both TDF and TED, the first